Logic Design, Chapter 3, Lecture 4. Hello, everyone. In the last chapter and in the last lecture, we have talked about algebraic manipulation. Why do we use algebraic manipulation? When we have larger gates or larger expressions, we can apply algebraic manipulation and we can try to optimize or simplify an expression so that we can have a minimum number of gates, minimum number of literals, and interconnect, so we can reduce the area, we can reduce the power consumption, and reduce the cost. Now, this is one of the methods that we use in logic design in order to simplify an expression. Now, in this chapter, Chapter 3, we are going to see another method, which we call it map method. So I will first give you a brief overview of what is a map method, and then we'll see different what number of variables and applying the map method to those variables. Now, we need gate level minimization, and as I already mentioned in the previous chapter, we have to optimize the logic implementation so that we can have an efficient implementation. And these type of optimizations, they're actually in the Boolean function, so we can reduce those Boolean functions to minimum number of gates and the minimum number of literals. So why do we need map method? Because we can have a complex digital logic gates, and these logic gates has got a complex algebraic expressions. So we can do a logic minimization. We can apply the Boolean algebra, but in chapter 2 we have seen some specific rules, but at some points they are not enough. So we need some alternative methods. So that's why Carnot maps were introduced. And Carnot maps is more like a visual way of optimizing a function. It's pretty straightforward. It's a pictorial form of a truth table, and it is applicable to a number of variables which are less than 7. Now, with the map method, one thing that you need to know, a diagram made up of squares, or you may call windows. And each square is actually representing one minterm. Okay, so when we combine these squares, which I will explain in a minute how, we can actually produce a simplified expression. And this simplified expression either is in the SOP form or POS form. Now, Boolean functions in general, they are sum of minterms or sum of products in the simplest form. They have a minimum number of terms or minimum number of literals, and the simplified expression may not be unique. So there can be an alternative way of implementing the same function, like we have seen it in the previous chapter when we were doing function 3 and function 4. Okay, so let's start with a simple example and with the two variable maps. Now, I will just translate this with the truth table. Let's say I have got input x and y and f. So 0, 0, 0, 1, 1, 0, and 1, 1. Now we'll have set of outputs, but how are those inputs and outputs are going to be translated? So 2 inputs means we have 4 possibilities. That means we need 4 squares in the K-map. I write x on one side and y on the other side. So this, the first row where x is 0, and first column where y is 0. Second row where x is 1, and second column where y is 1. So these are actually minterm 0, minterm 1, minterm 2, and minterm 3 are going to be mapped to these. Minterm 0, 0, 0, minterm 1, 0, 1, minterm 2, 1, 0, and minterm 3, 1, 1. So this is how we are going to get the details from the truth table or from an algebraic expression and map it to the K-map. So we can say that this is x prime, y prime. This is x prime, y. X is 0, y is 1. This is x, y prime, and this is x and y. Now, we are going to put those outputs into that map, and we will try to simplify it. So, for example, we have got a truth table, x, y, f, 0, 0, 0, 1, 1, 0, 1, 1. And I'm just giving random outputs over here, 1, 1, 0, 0. It can be any function. Now, let's try this with algebraic manipulation. So I'm going to use dark blue for algebraic manipulation without map. Now, with algebraic manipulation, we know where it is 1, right? On those two places. So f is equals x prime, y prime, or x prime, y. These are the min terms. Now, x's are common, x primes are common. So x prime is taken out. Y prime plus y. This is 1, and we ended up with x prime. So f is equals x prime. Now, this is the algebraic manipulation. Let's see the map method. So we need, let's try a different color. We need 4 squares, as we have got 2 variables over there. 2 to the power 2, 4. We have got x and y, where zeros and ones. This is minterm 0, minterm 1, minterm 2, minterm 3. I suggest you to write them, because when we have a bigger maps, it's easy to follow. So this is minterm 0, minterm 1, 2, and 3. In this case, minterm 0 is 1 and minterm 1 is 1. And the rest are zeros. So we have got 2 ones adjacent to each other. Now, the map method, this is the rule of the map method. We can combine the ones. We can either have the combination of 1, 2, 4, 8, 16, and it goes like that. So it's always powers of 2. Okay? Now, as we have got a 2 variable map, we can either have 1, 2, or 4 as a combination of ones. Now, I have got 2 adjacent ones. That means I can combine them like in a square. Now, how do we read this? This is important. How do we read this combination? We have to look at where the variable is not changing. So when we look at this row, x is 0 at this point, and x is 0 at this point. So I can say that f is always x is always 0. So I can say this is x prime. Then I have to check y as well. Now at this point, y is 0, At this one, y is 1. So I can see that y is changing. So I don't write that. So this is the rule. We look at the adjacent ones. We combine them, either 1, 2, 4, 8, or 16. And then I have to find out which ones are not changing, which variables are not changing. I look at x first, alphabetical order. X is 0, stays 0 in both of these squares for 1, but y is 0 and changes to 1. So I just write f is equals x prime. So as you can see, we got the same result as the algebraic manipulation. Now, this is showing us that rather than going through those steps, when you got used to with the K-maps, you can easily translate a truth table into a map, combine them, and write an expression. That's all you need to do. Okay, so the same example over here, x prime is the expression by using algebraic manipulation. Then we use those and we translate that into the K-map like we have done it over here. What is the largest rectangle that contains only ones? We always go for the maximum possible combination. You can combine them individually, but that's not going to give you a smaller circuitry or smaller expression. So what we do, we always go for the largest possible combination. When we have more, I'll show you how this is going to be done. So we combine those. This is x prime, where it is not changing, but y is changing from 0 to 1, 1 to 0 at this point when you do the combination. So I just write x prime. Now, that means f is equals x prime, and it does not depend on y. Here is another example, slightly changing the output f. So we have got A, B, F, 0, 0, 0, 1, 1, 0, 1, 1, and F is 1, 1, 0, 1. Right. We can write the algebraic manipulation, but let's do the map method. Again, we need 4 squares as we have got 2 variables, and those variables are A and B, where A is 0, A is 1, where B is 0, B is 1. Min term 0, min term 1, 2, 3. So min term 0, min term 1, min term 2, min term 3. Okay, so if we put those in, min term 0 is 1, min term 1 is 1, and min term 3 is 1. And min term 2 is 0. So we have got 2 possible combinations, which we have to cover all the ones. Okay? Now, we cannot have 3 of those together. We cannot do that. That's wrong. Because it's not power of 2, combination of 3. So let's get rid of that. We can do the same combination like we have done it before. We can combine those and say f is over there, is A is not changing, A prime is 0 at those 2 points, and B is changing from 0 to 1, 1 to 0. So I can say that this part is A prime. Then I'm just changing the color just to show the difference. Then I can do another combination because I want to cover that one as well. Rather than having a individual combination, as this is going to give you more literals, I can combine with the other one. So I will do those. So this will be 2. If I have a more combination, if I can make it 4, I'll go for 4. Now, I have to read this green one now. So when I look at A is first 0, but then changes to 1, or it can be 1 to 0. But when you look at B, it's always 1. It's not changing. So I can say the first rectangle showed me it's A prime. The second one, I'll say or F is going to be 1 when it is B. Okay? So A prime or B is the expression. Now let's try the algebraic manipulation. F is equals A prime, B prime, or A prime, B, or AB. 3 expressions I can get. Now, when you want to simplify it, I take A prime out, B prime B plus AB. B prime B is 1. Then I have got A prime plus AB. And I can multiply that out. A prime plus A prime plus B. This is gone as it is 1, and I ended up to A prime plus B. Now, you can see that I have ended my solution with 4 steps, but with the K-map, it's just put everything in and find out what is not changing. So based on the sum of the mean terms from the truth table, we can obtain using algebraic manipulation A prime plus B. And then we map it into a K-map. We identify our largest possible combinations. And we find out what is not changing, and we write the expression. It's pretty straightforward. And we are doing this either for 2 variable, 3 variable, 4 variable, 5 variable, even for 6 variable, you can go for it. Okay, so identifying rectangles in K-maps, this is the property. Rectangles that correspond to a product terms are restricted to contain number of squares that are power of 2, which I already mentioned. 1, 2, 4, 8. We cannot have 5, we cannot have 6, we cannot have 3, we cannot have 9. It has to be powers of 2. So the length of a side of a rectangle is also power of 2. Okay, so either it is 2 or it is going to be 4 or something like that. And goal 1, find the fewest such rectangles. So if you cover one and you don't need to cover it again, don't cover it. Okay? So if you can cover all the ones with one rectangle, do that. That will give you minimum number of product term or gates. And go for the largest possible rectangle. That will give you minimum number of literals. I will explain these with the examples as well. And goal 3 is, as I already said, rectangle is redundant if you are covering the same one in 2 different rectangles. Okay, let's go for 3 variable map. Now, with a 3 variable map, we are actually talking about x, y, z. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. and of course we will have f. Now, I'm just identifying minterm 0, 1, 2, 3, 4, 5, 6, and 7. Now, how are we going to map this into a K-map? As we have got three variables, we need to have 2 to the power 3, 8 squares. Now, how do we get these 8 squares? We can have 2 rows and 4 columns. So I write x on one side, 0 and 1, and I write y and z on the other one. Okay, so where y and z is 0, 0, 0, 1. Now the tricky point over here is that the next one is not going to be 1, 0. It is going to be 1, 1, and then 1, 0. This is another property of K-map. Why are we doing that? We want to do that because we are using a gray code over here. If you do remember gray code from chapter 1, we want to change one bit at a time so that each square is, we have gotten adjacent squares. So 0 is kept, the second one is changed. Second one is kept, the first one is changed. And the first one is kept, the second one is changed. Okay, so we are changing one bit at a time. Now in this case, 0, 0, let's change the color. 0, 0, 0 is minterm 0. 0, 0, 1 is minterm 1. 0, 1, 0 is minterm 2 over here. And 0, 1, 1, which is this one, it's going to be minterm 3. Then 1, 0, 0 is minterm 4. 1, 0, 1 is minterm 5. 1, 1, 0 is minterm 6. And 1, 1, 1, it's going to be minterm 7. That's all you need to know. Then, another thing that we need to know, and so that we can derive the expressions, how are we going to do the combinations? Now, combinations can be 4 of those. I'm going for the largest ones first. 4 of those, or maybe 8 of those if you have all ones over there, or maybe you can have a square, or maybe you can have the center square, okay, or maybe this is interesting, you can have the sides, okay, because these are adjacent to each other. So you can have the sides like that. In the end, it's formed like a rectangle when you combine that one and that one. So they are all acceptable. And as you can see, as we are using a gray code, these are all adjacent to each other. Okay, so for example, M5 and M7, they're next to each other. There's only one variable changing. So when we have got two ones over there, we can actually simplify it. Okay, let's see the first example. Simplify the Boolean function ABC. We have got 0, 1, 2, 3, 4, 5. Okay, I'm not going to write the question. I will directly go to the K-map. I need 8 squares. I know that. I have got variables A, B, C. So 0 and 1, 0, 0, 0, 1, 1, 1, 1, 0. I know my minterms 0, 1, 2, 3, 4, 5, 7, and 6. So which ones are going to be included? Minterm 0, minterm 1, 2, 3, 4, and 5. So these are the minterms that are covered in this function, which will give us output as 1, and the rest are zeros. So what will be the first combination? I can easily see that I can combine 0, 1, 2, and 3 like a huge rectangle. I cannot do this. I'll show you. I cannot do this as this is going to give me 6, which is not possible. It's not power of 2. So I'll go first this large or long rectangle, whatever you want to call. Now let's find out what is changing and what is not changing. If you look at it, A is 0, and all in this rectangle, it stays 0. So we can say that A prime should be definitely there, as it is not changing. But when we look at BC, it's changing from 0, 0 to 0, 1, 0, 1 to 1, 1, 1, 1 to 1, 0, or it can be other way around. So we don't write anything else. The first variable is A prime. Then we can have another combination, which you need to cover the other ones as well. We can do this for. You might ask, why are we not doing this? Only 2. As I already mentioned over here in the slides, find largest possible rectangles. You can get minimum number of literals. 2 I can go, but I can go for 4. Let's go for 4. So I'll cover those 4 together. And I'll just put or sign in between, and when I combine those 4 together, I can see that in this rectangle, A is 0 changing to 1. So I don't write A. By the way, this is A prime. We should not forget to write that because of that. Now, A is changing 0 to 1 at this point. What is not changing? B is 0, stays 0. C is 0, changing it to 1. So I can clearly see that B is always 0. So I can say this is B prime. That's it. This will give us the solution.